distinguished guests, esteemed academics, ladies and gentlemen. It's with immense pleasure that we welcome you all to the 44th edition of the Inaugural Lecture Series brought forward by the Faculty of Graduate Studies, University of Moradoo. Without further ado, let's commence the day's proceedings. To officially commence the day's proceedings, by introducing the professor for the day, Professor Subha Fernando, Department of Computational Mathematics, Faculty of Information Technology, University of Moradoo, I very respectfully invite the Dr. Thirini Thiyatidaka, Head of the Computational Mathematics, Faculty of Information Technology, University of Moradoo.
Good afternoon, everyone. The Faculty of Information Technology, distinguished guests, colleagues, and my dear students. It is my great pleasure to welcome you all to this lecture titled From Algorithms to Impact, Building Human-Centered Artificial Intelligence for Society and Industry. Artificial intelligence is changing the way we live and work. However, the real value of AI lies in using it to solve real-world problems and improve people's lives. Today, Professor Subha Fernando, a professor in artificial intelligence attached to the Department of Computational Mathematics, Faculty of Information Technology, University of Moradoo, will share insights on how AI research can be transformed into practical solutions that create positive impact for society and industry. We are delighted to have Professor Subha Fernando with us today and look forward to an informative and inspiring lecture. Professor Fernando obtained her Bachelor of Science degree from University of Columbia and subsequently earned both her Master of Engineering and Doctor of Engineering degrees from Nagaoka University of Technology, Japan. She is an accomplished academic, researcher, technology leader, and industry consultant with expertise in multi-agent systems, evolutionary computing, optimization, reinforcement learning, deep learning, digital twins, decision intelligence, and human-centered artificial intelligence. Throughout her academic career, Professor Fernando has received several awards and recognitions for her contributions to research, innovation, teaching, and the advancement of artificial intelligence. Alongside her academic work, she has served as an AI consultant and advisor to organizations across multiple industries, contributing to intelligent solutions in autonomous systems, logistics, transportation, healthcare, finance, and complex operational decision-making. Her work focuses on transforming advanced AI algorithms into practical, responsible, and impactful solutions for real-world challenges. A central theme for her research is developing intelligent systems that move beyond prediction to support adaptation, optimization, and effective human decision-making under uncertainty and disruption. In today's professor's talk, titled From Algorithms to Impact, Building Human-Centered Artificial Intelligence for Society and Industry, Professor Fernando will share her research contributions, industry experience, and vision for creating trusted and impactful AI technologies that bridge cutting-edge research with practical applications across society and industry. Please join me in warmly welcoming Professor Subha Fernando. Madam, over to you first.
Thank you for having me today. I'm the Dean of the Faculty and the former Dean of the Faculty, the Senior Professor of IT, my major, Professor Subha Fernando, and also the Vice Principal, and the colleagues of the department and the online participants. Thank you for joining this lecture. let me walk you through the journey from algorithms to impact. I'm trying to take you through how AI building blocks can embed it into IT systems that genuinely help people to make better decisions. So the whole argument of these presentations today is that the algorithms alone is not that impactful. So we have to embed them engineered properly inside the IT systems so the benefit of the society and industry. So the conceptual foundation of human-centered AI, I will take you through how the optimization can drive the intelligence for complex and real-world systems. So let's see how we have this so far. So we are starting with the symbolic AI, the logics, rules, and especially the expert systems and fuzzy logic systems, where the knowledge was represented as structured format, but we had a problem of how it works with the dynamic conditions and different uncertainties. But however it is today, the expert systems and fuzzy expert systems are now being connected with the gradient learning algorithms, and with the support of generative AI, they have also become very powerful today. And then we started the machine learning algorithms, listening to the patterns of the data and initiate the probabilities of falling into different classes based on the activated patterns on the input, based on the input you apply. So then we start the classification and clustering, and then we move to the deep learning, that where in the machine learning, we had a problem of manual feature engineering, and then we move to the automated feature engineering with thanks to the convolution operation and the gated neurons. We could do, to some extent, vision understanding and speech translations, but we were really good in image recognition and object detections, thanks to UNet and diffusion models. And today is the era of generative AI that mostly the people are talking about, which is more into the conversational part of SIC, because all the last few technologies we are discussing was mainly we had a problem of understanding the language, speech, and images or the videos. Our perception from our model's perspective was not very well defined and understandable. So therefore, we had a problem of connecting with the humans' interfaces and connecting with the systems that generate text, and that's what with the text, documents, images, and videos. So therefore, with the conversational improvements with the generative AI, today we are able to understand the text, images, and videos as well. So it has improved the perception of the models. So the understanding of customer intents now are being clear, and also the understanding of what the image and the video is talking about has been clear. So it's now the time is Industry 5.0, where we are talking about the human-centered artificial intelligence, where the point terms decision intelligence comes in. So far what we have done when looking back at symbolics to the generative AI, we have been able to do the classifications, clustering, and mainly decision support systems, recommended systems, and generative, when it comes to the understanding of generative, it's again the perception understanding. So what actually we want is something beyond the predictions. That's where the help we can give the humans to make a better decisions in complex environments. The prediction is important, but it doesn't drive us to take the better decisions when the environment becomes so dynamic and complex. So why we are talking about now is that AI is no longer restricted to laboratories, universities. Now it has gone to the public. The people, the normal person who doesn't know anything about coding can still do the coding by prompting. The reason behind looking for the decision intelligence is now the understanding is possible. So you should be able to understand what the client end wants. So as a system, how can I help you with me to make a better decisions? That's what the society and industry is asking. So if it takes the society, how the people travel, how the patients are monitored, and how services reach citizens have been completely changed. And also the industries like logistics and manufacturing has been completely changed. They have gone to the level of monitoring the individual package, tracking them to the geo level, and understanding and giving the customer view of where the package is, who is carrying what, and who is the rider, and which vehicle it is in, and so on. So all the details present in the labels of the packages, addresses, names, whatever the compliances, security conditions. Now we can understand, thanks to the generative AI and deep learning technologies. But what remains is, can we help with these people or these industries with the more intelligence that help them to make better decisions when the business process is in executions? So having the data, you can give the insights, but giving the decisions to take the actions is the most practical and impactful when it comes to the industry applications. So the value begins when the insights become actions in the real world. For example, if you want to predict a route is overcrowded, and probably you have multiple choices. One could be allocating the right number of buses, or someone say it is very easy, but you have to understand they have the resource limitations. The resource limitations such as the driver's availability, the vehicle's availability, timetables, everything, constraints and condition the actions to be triggered once such insights made. So which choices to make is up to the human experts sitting in this loop. What the system can do is help this person to find the better choice based on his KPI or his objective functions. So the ultimate goal of my argument is that to make the AI impactful, it must be designed carefully in IT systems, engineered properly as algorithms that work smoothly with the business processes. That's where the human can actually benefit of when executing them. So in this process, we do not discuss about something human to be replaced, because it's very difficult to completely replace the whole task of a human being by a system. We are here to empower them and support the humans who can make better choices at the industry. So if it takes the decision processes, for an example, let's assume you plan a wonderful plan of bus transport intelligence systems and deploy the fleet in the field. All of a sudden, the couple of accidents happen, and you find, and the entire road flows. So what are you going to do? So in such cases, how much you plan, how much you predict, the disruptions definitely will happen with certain probability. So the preventive mechanisms are possible if you know it beforehand. Otherwise, you have to get ready for the disruptions. So When it comes to these kind of operational environments, where the uncertainty is very high, we cannot no longer work with the predictions only. We have to work with the operational constraints and figure out as a system that embedded AI building blocks inside. How can I help this person to solve this problem? What is his KPIs? It could be looking for the options of reduction of cost, meeting or the cutting down of passenger waiting time. He could be looking for the options of derouting the previously deployed fleets to additional areas. There are multiple choices he can come up with. But he also has problems of conditions and constraints, where when he executing this decision, some of those choices would not be feasible, it could be infeasible. For example, if you have only 10 drivers, all the drivers are in the route now, you don't have more drivers to deploy. So adding a vehicle doesn't make sense when it comes to this decision process. So therefore, my whole argument in decision intelligence is predicting an outcome is very important. It gives the insights, but doesn't solve the problem. The prediction always tells us what may happen, but decision intelligence is the one mostly tells us what to do next. So if somebody predicts very easily, there is a demand on this particular route, there is a rise of demand sharply between 7 to 9 a.m. in the morning on weekdays, a particular day due to the event suddenly has been organized. What are your alternatives? Obviously, you can initiate a different timetable, changing the frequency of bus leaving the depot, or different routes can be introduced, or additional routes can be introduced. You can add a different number of additional buses and deploy standbys, or completely redesign the entire bus schedules that also overwriting the non-impacted area. There are multiple choices, but the question here is, which choice is the best, will give you the best outcome under the conditions and constraints you have? You have multiple objective functions in your hand to optimize. One is minimize the customer waiting time or the passenger waiting time. Other one could be the maximize the vehicle utilization, driving utilizations. And in Europe, they are looking for to minimize the carbon dioxide minimization also. And after all, it's a business. They want to maximize the revenue. So by considering all this, someone would say, okay, for that day only, why don't you deploy additional buses? But it could be the most easiest adaptive probability, the solution. But the problem here is that it could be infeasible if you have a less number of drivers than the buses. Because the drivers don't drive every day. They need also the compliances. So the optimization is always the bridge between what you predict and what you execute. If you bring and connect them both together, you get the better intelligence where the decision can be driven under optimization of many objectives all at once. But the problem here is there is no single winner. The problem is none of the real world decisions almost come with a single goal. They come with the multiple competitive goals. If there's a multiple competing goals, there is no single winner for this problem. When you optimize or minimize the customer waiting time, other side, it will maximize or minimize your vehicle utilization. Because to meet the customer demand, you might need to deploy more vehicles or buses that will reduce your revenue because you are increasing the cost of managing the fleet. So the human-centered AI is not a philosophical concept. It can be grounded very well on real-world applications. If you have done and engineered properly the scheduling, the routing, and planning properly into these systems, where the adaptive decision-making become possible under different uncertain conditions. So in this process of, when you have a menu of non-dominated trade-off or competing goals, the finding the best choice under your KPI preferences under different conditions and constraints is always the problem. We are in mathematics, in evolutionary, we are discussing the non-dominated solutions. So the non-dominated solutions are the one that perform in one aspect better than the others. But if you take the points A and B and C in this graph, the B is somewhat balanced. It has somewhat okay waiting time and the cost. But if someone taken the cost, it has completely maximized the cost and minimized the waiting time. So if somebody wants to execute an action, that's where it will minimize the waiting time. Definitely it will increase the number of vehicles you deploy in the environment and increase the cost. At the same time, if you get into the point A, so that you have a minimum cost but high waiting time. So in this optimization process, we have thousands of options. They are equally valid ones under different KPI combinations, optimizations. So that it is the human in the loop to take which decision of which trade-off should be considered. So if you take a plan is created when it comes to the scheduling in supply chain management, logistics, transportations, fleet management, very dynamic and complex real-world scenarios. Thousands of packages delivered on a day by limited vehicles to meet the customer committed windows with the minimum violation of SLAs to take the maximum revenue. So somebody has to come up with a plan, a very good plan of satisfying all these constraints. The person is in the balance of multiple objectives, optimizations, cost, meeting the SLAs, meeting the customer commitments, reduce the waiting time, and optimize the use of vehicles for the fleets. So once such plan is created, when at the moment it is being executed, we call plan is running. When the plan is running, there is always possibility of disturbance. There are all of a sudden a vehicle breakdown, customer changes the window, then the plan doesn't work thereafter. So there are disturbances that we have to react. That is, at the time of the execution, we have to quickly respond and replan. There are disturbances we can forecast before it's being executed, and then we can predict and replan. However, the replanning is required. So to support this entire conceptual foundation of human-centered AI and decision intelligence, there are four building blocks of artificial intelligence playing a key roles. One is multi-agent systems. The second one is evolutionary algorithms. Third is gratifications or greedy heuristics. That's looking for the local optimists. And the fourth one is the digital twin. Let's see one by one. Agencies. I call agencies autonomous. When they make their decision by themselves and they come up with the plan by themselves based on the actions they are constrained to. So the agents has to come up with a plan from the feasible set of actions, understanding the current context, and bring us a plan that can be feasibly executed on the environment. When such an agency in place, what's important is when it's become multiple agents who have the negotiation capabilities, then the decision will be distributed, or the intelligence must be distributed to collective intelligence, generate the collective intelligence. So when this collective intelligence is there, the agency can represent individual entity in the real world with own characteristics and its own policies and violations and constraints and conditions. It could be a vehicle that's suited only for traveling in A4 routes. It cannot travel A2 or A1 routes. So it has its own conditions. And also it has the capacity size, how many load it can carry. And based on its all vehicle condition, it could travel distance, short distance or longer distances. So that agency is very important when we need the decentralized decisions to be taken. And there the collective intelligence will play a bigger role when it comes to the multi-agent systems. So I'll touch upon the technology side of architectural support. So the agent systems, when it comes to the multi-agent systems, you can consider as a separate service or the normal modular service, or as the entire multi-agent system, you can containerize into a service. But the question here is how many agents you create. If you create thousands of agents, putting them into one container, it's not feasible, it's not executable in IT environments. And if you put it into a single container, single agent, it will consume a lot of computational resources. So we have to keep in mind whether we go for microservice architecture or whether we go for containerized architecture with the pods concept. So that's whether the entire multi-agent system will be inside or single agents, or we have to go with the snapshot idea. We'll discuss it later. And of course, this agency needs to listen to the environment to understand which part of the environment has been impacted. So there should be an event triggered from some kind of a registry or that represent the world state. And probably the options will be Kafka. And the registry and the world state could be the digital twin. When it comes to multi-agent systems, we have both the options of having global optimizations as well as local optimizations. If you have a very limited number of packages like 500 then global optimizations with the multi-agent system is a feasible IT solution. But if it is go to 3000 knot, it's not feasible with the multi-agent systems. It's not impossible, but embedding them into IT system is quite a challenge. And the second one is the most important, that is the backbone of this entire decision intelligence grounding concepts. That's the evolutionary algorithm. We have been discussing in artificial intelligence for a long period of our evolutionary algorithms as genetic evolutionary strategies, evolutionary programming, and so on. The key importance of evolutionary algorithm is it is meta-heuristic such algorithms. That's where that have the ability to bring the balance between explorations and exploitation. So this is a population-based algorithm that's where we call of these non-dominated solutions can be found by using this exploration and exploitations of evolutionary algorithms. This can be used to solve NP-hard problem, which is when the number of volumes increases or the number of packages increases and the number of vehicles, drivers increases to the 5,000s of huge networks that's covered multiple countries, then it's become a combinatorial problem, and then it's become NP complex. So when it's become NP complex, finding the solution from mathematical approaches is possible, but it's become very, very expensive to calculate. So what evolutionary brings us to the table is intelligent approximation. It doesn't guarantee you get the optimal solution, but it will bring you a better solution within a couple of minutes. So when it comes to the technology of such algorithms, so it's important for us it's a back-end process. If we go for live systems as an online process, it will be heavy duty process. So probably the options could be you have to improve the evolutionary in such a way that where the multi-populations are possible. Imagine you are asked to find the plan to distribute 5,000 of odd packages of 150 of routes with the 200 vehicles, given that different shapes and different capabilities, and the packages could be in different requirements. It could be temperature sensitive, it could be hazard items, so the certain cargo types could not match together to travel. So in such cases, such NP complex problems will definitely need evolutionary algorithms help. But in such cases, how the IT should be engineered to bring that algorithms into the system is a real engineering challenge. So you can think it of as subpopulations of evolutionary algorithms, and you can think of it as compute-heavy and asynchronous processes. But ultimately, what is important for us to have the best plan out of it to where these competitive KPIs have been optimized under the given constraints and conditions, and where we can have handful of non-dominated solutions that satisfy these requirements. So why did I say it is a really hard task of bringing the evolutionary algorithm to systems? Because evolutionary is a very general. Anybody can adapt it. anybody can implement it. The AI challenge is how you define the crossover operations. How do you define the chromosomes to represent the solutions? And what mutations and crossover operations you will apply to bring these feasible solutions to the table. That is the problem. So if you take the job scheduling, the same job cannot happen to be in the different schedules. It should be in the one timetable, not in multiple operated timetables. So it's a combinatorial problem again. So you have to have the order preserved. Certain jobs you need to be executed before executing the other job. There might be prerequisites. So all these things need to be considered when you are developing this plan. Finally, let's assume you have represented this problem somehow in chromosomes and identified the crossover and mutation operations. So how can I drive this evolutionary algorithm to find the optimal solutions or non-dominated solutions? In literature, we have three prominent algorithms. Non-dominated sorting genetic algorithm, that is NSDA2. That's discussing this Pareto rank and Pareto front, the same as the non-dominated solutions of first rank. And the third one, that's where LHFID, that's talking about how the human preference will also impact it and reach the convergence of identifying these Pareto optimal solutions or the Pareto fronts. Right, so now the plan is ready. We have the agency pool that ready to absorb any events that triggered from the environment. The question is when the disruption happens, when the planning execution. So we have two options when the planning execution. Completely replan the entire plan and redeploy the fleet, which is impossible. It's in the execution means to some extent it has been executed and almost all packages, sometimes 50% has been delivered. So what we could do is the replanning. The replanning only to the impacted area. But this replanning should happen very rapidly. If you take hours and 2 hours to do the replanning, it will definitely collapse the entire plan. So the quick response is important, but also how you're going to replan the impacted area with the minimum cost is also very important. So in these cases, where we need the local optimizations, we cannot look for global optimizations. We have to work with nearby local optimizations in our KPI surface and look for the Pareto front look for optimal solutions that where our multi-agent systems can bring it us through the negotiations under their distributed intelligence. So finally, the digital twin is the most important part of this concept, which creates the blueprint of physical world to the virtual world or the digital world. If you don't see this snapshot every minute live, you have no clue of what is happening in the ground. So if the ground being replicated as it is, simulated as it is in the digital world, then we can do two things. One thing is, before something to be happen, we can simulate on that snapshot at that time and see how the plan will respond which part will fail. The second thing, if the actually failure happen at the live, then of course, by help with this digital twin concept, deploying the multi-agent system on top of it, we can quickly come to a local optimum solutions. So this is how the plans, when it is in execution, will be reflected to the digital world by using the concept of digital twin, and any event triggered in the physical world that need the attention of the system will be implied in the digital twin for the multi-agent system to act on that and find a local optimizer and do the replanning for the impacted area and execute back to the, or recommend back to the human ego. So in each phase, play a key role: planning, evolutionary algorithms, executions, and simulation, digital twin, disruptions, multi-agent systems. Predictions will do the preventive mechanisms of understanding early detections or classifying early faults. And finally, you comes to the phase of human-centered decisions by giving the proper recommendation on action, a pool of actions under different KPI combinations, with the Pareto front of solutions, which one to choose is to decide by the human in the loop. So I think I explained this one. So this recommendation, people think it's product recommendations, music recommendations. This is not such recommendation engine we're talking about. We are talking about the decision engine, which recommend the decision for the execution in real world under the condition and constraints defined by the business process and optimized under the KPIs given by the business process. The planning has been executed and replanning also been executed, making the feasible solution possible for human to recommend and find the final goal of the business requirements. So it's not just positioning and action. This action is feasible on execution on the environment as it is, but it needs the recommendation of the human in the loop, because the choice of which Pareto front will be chosen for this scenario is completely the responsibility of the human. So in this technology stack, usually people ask, where generative, where agentic AI, that is the buzzword. So, but what I see generative AI is a stochastic probabilistic machines that release the tokens, conditions to the pattern activated via context. So these generative models has, as I said in the beginning, make us enable to understand human inputs, making a conversation with the humans or any other systems with the language, natural language, or the images can be understandable, videos can be understandable. So in any of this stack, that's where we need the conversation with the human, or understanding the external knowledge. Generative will help, and agentic AI will help when we want to execute very well defined workflows. That's where we have already pre-planned. It's a routine task that a person is doing, where the agent can just trigger it out by calling an API or executing a workflow. What's very important here is to have the optimization intelligence and the human decision layer. So I have listed out 3 use cases for you to explain these concepts more clearly. Just brief, very brief. So that's how the why prediction is important and how we make it to the next step of optimization and action recommendations actually to replace or actually to solve complex business problems. So the first one is decision intelligence for public bus systems. So the people think it's just allocating buses to the routes. It's not that simple. The particular route is so crowded, then what are the possible actions you can take? Is always the questions. So the number of buses you have in your depot, the number of drivers available on that day, and the buses have in the depot also matters. You can't just deploy another bus to the route if there is no such demand for the rest of the buses. Minimizing customer waiting time is also important. At the same time, to business to run, maximization of the revenue is also important. So therefore, let's assume you have a very well planned and executed. All of a sudden, the road is closed. What you should do? So probably we will wait in Asia, but in Europe, they want replanning the routes immediately. Reduce and minimize the waiting time of the passengers. So what are the options do we have in such cases? Quick local optimization, localized to the impacted area is very, very important under different KPIs. So doing so, the human impact is shorter waiting time, more reliable journeys, and better access to mobility and so on. The business point of view, higher vehicle utilizations, data-driven route planning and scheduling, and faster disruption recovery is the important thing. The second example is coming from logistic and fleet intelligence, where you see NP complex in real world, deploying or dispatching 5,000 of packages over multiple countries over a night of 24 hours from multiple depots, meeting the customer windows. Still, you have to make the revenue and managing the number of vehicles and drivers you have under all the compliances from the government. So it's not just planning. You have to have your KPI optimized and identify the Pareto front properly, optimal solutions, and choose the one that suits you for the best case for you. And in the execution, how much you try, it'll fail. Somewhere something will happen. The disruption recovery is utterly important. So the same outcome for the industry, higher fleet utilization and safer driver workloads, reduce empty mileages, improve delivery reliability. The people think it's all about the logistic and supply chain and transportations. No, it's not. It's also about the optimizing the pricing slots and meet the capacity. Sometimes you don't have vehicles or the resources to meet the demand. Then obviously other strategies should work out. So giving different time slots with the different discount patterns or different pricings, that's also part of the plan. So the people who have paid additional prices to meet that particular delivery slot, that is a mandatory requirement or the hard constraint we should satisfy. So it is not just transportation and the resources, but also it could be go to the complexity level of managing the delivery time slots based on the customer requirement or priority. So in this, there are multiple business impacts, revenue from premium slots. The business can gain revenue out of that doing so, and also better demand distribution, unnecessary to don't get congested on peak time overloads. Improve choice and conversations, and control SLA compliance. Okay, in conclusions, the intelligence becomes important and it's become impact when it reaches the decision. From the mathematics of the search of meta-heuristic to the architecture that runs it in a human choice. This is not simple a toolkit. Each phase is very important to move to the next phase. The final decision of which action or which paragraph front should be executed finally in the hand of the human. That choice is based on his KPI preferences. And that is the human-centered AI. That's in Industry 5.0. Right, I think that's all the software references we have used. And thank you very much.
A heartfelt gratitude to Professor Subha Fernando for that insightful and compelling lecture. Your expertise and the insights shared with us have undoubtedly broadened our understanding of the topic. So we are truly grateful for Professor Subha Fernando. As a token of appreciation for Professor Subha Fernando for your valuable contribution to this inaugural lecture series, we very respectfully invite Professor Ashoka Karunananda, Senior Professor, Department of Computational Mathematics, Faculty of Information Technology, University of Molecule, to present the lecture memento. Dear Professor Subha Fernando, please accept this lecture memento. Thank you very much, Professor Subha Fernando and Professor Ashoka Karunananda. With that, ladies and gentlemen, we are moving to the conclusion of this session. Before we conclude, we would like to express our sincere gratitude to our sponsors, Cargill's Private Limited, our event sponsor, Daily our print media sponsor, and Sri Lankan Scientists, our social media sponsor. Once again, a heartfelt thanks to our sponsors. With that, we officially bring the 44th inaugural lecture to a close. Thank you very much for being such an engaging audience today. Looking forward to meeting you all in the 45th edition of the inaugural lecture series. Have a nice day.